All right, I guess we're going now. Hello, everybody.
Yeah.
Welcome back to Astro Coffee Hangout. My name is Tony Darnell from deepastronomy.space, and today we are going to be talking about, well, maybe there's a crisis in cosmology, but maybe not. We're going to talk about that. My guest today, you guys have met him before, Dr. Brian Keating. He is a professor of physics at the University of California, San Diego. He's also the author of the book, Losing the Nobel Prize, A Story of Cosmology, Ambition, and the Perils of Science's Mightiest Honor. There's a link to that in the description box, and there's also a link to Brian's channel. And before I bring him on, I just want you to say at the top of this hangout, I want to say to you guys, you really need to follow his channel because he has got some great content where he interviews all the big guys. I mean, just getting ready for this hangout, he sent me a link about where he had talked with Adam Riess about this very topic earlier. And Adam Riess, as you may know, won the Nobel Prize for physics in his work on Type 1a supernova, where they actually, among others, where they discussed or where they discovered the expansion or the acceleration of the expansion rate of the universe. So, and he's talked with Freeman Dyson, he's talked with all kinds of Sean Carroll, all these guys that I admire, and so you really need to follow his channel. He's got some great content. If you don't, the link to his channel is in the description box. You can also follow him at Dr. Brian Keating. So let me bring him up. Taking precautions, are you, Brian?
Yeah. Well, you told me you want to speak about the co-crisis. I don't know if that was cosmology crisis or
I was
some
pretty
other
clear.
crisis.
I'm sorry, but I was pretty clear. Cosmology.
Oh, okay. All right.
Can't be too safe these days.
Hi, everybody.
Hey, Brian, it's good to have
Just
you back.
having a little fun. Don't send me any hate
You're
mails.
getting the
But
hate. You can't do anything online without getting hate, man. It's gonna happen.
I know.
Yeah. So, I love the fact that you are available for these hangouts because when there's so many things in cosmology that I'm personally interested in. It's my favorite topic. It's one that I do the most content on, and so we've already talked about things like inflation. You've helped set us straight on that, but I want to talk a little bit about this issue in cosmology right now, where we are measuring the large-scale structure of the universe in ways and with accuracies that we've never had before. And we are learning a lot about what the universe is like, how old it is, and all kinds of things. But one of the most important parameters that we're trying to nail down is the rate at which the universe is expanding. And so before we get into the crisis part of it, maybe we should talk a little bit about the Hubble constant itself, what it is, and is it really a constant, and stuff like that. So can you give us a background on the Hubble constant itself, or the Hubble's
Yeah,
maybe is a better
that's
way?
great. And I want to say, Tony, thank you so much for having me on. You are one of the few channels that I actually patronize, not just with subscriptions and notifications, but also via Patreon.
That's true,
because I
you
think
do,
we need to
and thank you, man.
Yeah.
He does, and so please follow his lead.
Yeah.
Everyone.
Yeah.
It's okay.
It's just,
I need it.
it's $800 a month. It's not a big deal out there. Please,
It's not $800.
Tony needs a new, he needs a new Tesla. Okay.
I needed a
get
video
it for
capture
cheap.
card, I can tell you that.
That's right. No, but it costs money to do it, and you're a consummate professional. So thank you so much for allowing me to come back. I love your guests.
welcome
I always
always,
get
dude.
tons of follows and friends on Twitter, and some of them may know this and can verify. I will send you stuff. I send out lovely meteorites like these here. Sometimes I send out pieces of lunar surface, which I've sent to some of your followers, which I've gleaned from your channel. So thank you so much, Tony. So what is the Hubble constant? What is the Hubble constant, and why is it causing this controversy and this crisis, which is really one of the most exciting debates that's going on in cosmology? And in my book, I talk about what I call the 5 great debates, ranging from is the Earth the center of the universe to is the universe the center of the multiverse? But really, I say that the controversies and debates will never end in cosmology. And I think that's why you like it and other people like it, because there's always something fascinating,
Brian,
something debatable.
I have to interrupt you, dude. We got bad sound. It's coming from Okay, so here's what's happening, folks. I am trying a new connection method. I had a video capture card go down that lets me use Zoom. I use Zoom on a different computer because I don't have enough bandwidth on this computer to do both streaming and the Zoom meeting, and it died today. And so I'm trying a new connection method for Brian, and I'm still working out the sound. So I'm sorry about that. Let me. If I don't get it sorted, we're going to have to do this another time. Let's see. Let's see here. Just stand by, folks, while I look and make sure my.
I think you sound good, right? Everybody.
Yeah, am I sounding
That's
okay,
fine.
guys? Is it just Brian, because I've got him patched through the. All right, he's using this. Okay, Brian, give me a test sound.
Okay, 1, 2, 3.
All right, let me try something. All right. And it figures I have a really short cord for this. All right. Can you try it for me now, Brian?
Yeah. 1, 2, 3, 4, 4, 3, 2, 1.
All right. How is that, guys? Is he sounding better? I patched him in to the.
People are saying that.
I had to really severely mess up my setup here. All right. Okay, Han. Okay. So, give us one more test.
Yeah. How about this? 1, 2, 3, 4, 4, 3, 2, 1.
All right. Let me know, guys, on the chat how we sound here. Thanks for your patience on this. Brian has an echo, but it's gone. Okay, well, he had an echo. Does he still have an echo is what I'm trying to find out. Odd reverb on. Better.
1, 2, 3, 4. Crisis. Crisis 2020.
All right.
Cosmo Crisis.
All right. Testing. All right. Still has an echo. Oh, boy. All right, guys.
1, 2, 3, 4.
Damn it. This is really too
I'm
bad.
hearing, I'm listening in on. Yeah, there's some feedback, but tell your friend threshold. No echo. Some are saying no echo. Some are. And on YouTube.
So somewhere I've got something on that's being monitored. Let me just try this, and let me go here. All right, try it one more time for me, Brian.
1, 2, 3, 4. 4, 3, 2, 1.
All right, so the levels are fine. I had a monitor on that. The echo is still the problem. The echo for Brian, correct? Not for me, right, ASCII? One more time, Brian.
1, 2, 3. 3, 2, 1.
All right. Poop. Oh well. I got to get this sorted. I think I'll sit here and do it on a Hangout. Yeah, I know the problem is, like I said, he's connecting via Wirecast, this thing that they give me, but it's somehow no, a little bit better. Do you have any speakers on at all, Brian?
I just have. I should just have this speaker. I don't hear an echo on my channel.
I don't hear you.
I
don't hear you I don't hear the echo in mine.
headphones.
When I'm talking to you
so
over the
everything's off now.
session, I don't hear the echo.
Right.
This is better. Brian he is using his headset. This isn't Zoom, Peter. That's the problem. If it were Zoom, I could fix it.
Yeah, I'm using this microphone.
All right, Andy says you've got the headphones are on and the monitor mic is on. All right, I've got...
Let me try the monitor. I'll try turning off the monitor. I definitely have the monitor mic off. Let's try one more time. Jabber Pro is the built-in. That's the input. Output is through the headset. So, you know what? I can try let me try the built-in microphone. Might be hard to hear.
I actually don't think it's you. I
me?
think it's me. I think somehow I've got monitors going and being brought. Two things are being broadcast. All right. All right. How are these levels? Testing. 1, 2, 3. We're not going to keep doing this, folks. I'm going to keep at it for a few more minutes, and I'm going to stop. We might have to do this later. Somehow I've got Brian's voice in two places. All right.
1, 2, 3, 4.
One more time, Brian.
1, 2, 3, 4. 4, 3, 2, 1.
Okay, can you try it again?
1, 2, 3, 4. 4, 3, 2, 1.
We hear them in real time and with the latency delay. All right. One more. Okay, let's see. There's a delay between when we're broadcasting and when I see the chat. So do one more test, Brian. Just say.
Okay. 1, 2, 3, 4.
Yeah.
4, 3, 2, 1.
All right. All right, I will try one more thing.
Let me try one last thing. Try turning off my headset just in case it is mine. Can you hear me?
All right. Isn't this fun, guys? All right. Nope, I don't hear you now at all. Testing. 1, 2. I don't hear you at all now, Mike or Brian. Okay, well, let's not waste everybody's time on it. I'll get it. We'll have to get it sorted. It's only happening. It's only happening when I'm broadcasting because I don't hear any of this in our session together.
Yeah.
So it's whatever's getting something that's getting broadcast twice. I blame Wirecast. I don't think it's you. It's got to be a setting I've got here on Wirecast. So it's broadcasting two things at once.
Oh, okay.
That's got to be what it is. I've got two. I've either got a monitor on. I've turned off every monitor I can find.
Yeah, I mean, you sound fine to me. Yeah.
Mm-hmm. Yeah. And let me just do. Let's see if. Yep, that's off. Hello, testing. Nope, I'll turn that off. Then nothing works.
1, 2, 3, 4.
Okay.
1, 2, 3, 4.
All right.
Okay, still bad. Everybody's saying it's still bad distancing.
All right.
I can just hear Brian.
Yeah, everybody's. It's not a YouTube issue, Jack. Jake. It's got to be me. Got 70 people watching us figure this out.
Yeah. Touch the mic.
Oh, fun. Well, this is just the nature of. Okay, guys, I think I'm going to stop the stream. Um, and we. Oh, it's better. Solved. Better. Is it solved or better? There's a
Better
difference
one,
between
two,
those
three,
two.
four. I don't know. If you
No
can do
echo
nothing and solve
now.
the
I
problem.
can hear Brian
One,
fine.
two,
Better.
three, four.
Oh, yay!
Peter, what about you? Peter, can you hear us?
Yeah. What about Peter, John,
Peter.
everybody? Tell us what we got. Sounded better.
All right.
All right. Everybody's
Test it
saying it's
again.
better. So let's.
Brian, that's better. Just Brian. Oh, so I'm echoing.
Sounds good now.
1, 2, 3, 4.
Works now. ASCII says works now.
All
Okay,
right.
Gaming Fish Guy, thank you. I gotta ask about that handle someday. All right,
It's fixed.
thank you.
Okay.
Okay.
All right. Well,
Now
we'll keep going.
start again. Start again. All right.
All right.
We're talking about the Hubble. I think we're talking about the Hubble constant. Hell, I don't know anymore.
Yeah, we started talking
all right.
about what is Hubble. Yeah.
Would
who
you
is Hubble?
mind giving us, please, Brian, a
Yeah, we're
introduction
talking about
into
Hubble.
what
Who is Hubble?
what the thing
Yeah.
is the universe. I don't even know anymore. Just pick up where you were on Hubble constant. Take do.
Okay. All right. Here we go. So, first of all, Hubble constant. What is it? What does it do? Why is it important? Every field has sort of its master quantity, its master parameter, the thing for which it depends on which it depends. And for example, for Einstein's theory of special relativity, it's c, the speed of light, 300,000 kilometers per second. In Newton's gravity, in his equation of gravity, there's capital G, which is the relates the amount of acceleration, of force felt by two objects of a given mass at a given distance. For cosmology, cosmology's master parameter is called the Hubble constant, and it's related to something called the Hubble parameter in the special case that it's evaluated of something that varies over cosmic history, and it's evaluated as it is today. So how fast is the universe expanding at this very moment? That is the sort of master parameter on which everything in cosmology depends. So it's critically important to get it right. And for many decades, even almost 100 years now, this constant's been measured by people ranging back to Edwin Hubble himself, after whom the constant and the parameter takes its name. So he discovered it when he was looking at distant galaxies, and he made the observation that with a handful, literally a handful of exceptions, all of the hundreds and millions and hundreds of billions, perhaps, of galaxies in our observable universe, they're all moving away from us. And the rate at which they're moving away from us is dependent on how far away they are from us. So everything is moving away from us, with the exception of the very closest galaxies like Andromeda, the Magellanic Clouds, which are not expanding along with the universe in the so-called Hubble flow, but instead are gravitationally bound to us. So with those literal handful of exceptions, every other galaxy in the universe is moving away from us. So he got this from observations given to him by a friend and colleague, Vesto Slipher. Some say that good old Vesto had the data to make this law up even before Hubble, but it's generally credited to him. And it states the very simple supposition that the redshift, the amount of stretching of the wavelength of light, depends on as a linear function of the distance to a given object. And so the stretching is not unlike the Doppler shift that you hear when an ambulance drives by you. As it comes closer to you, the frequency gets increased. The pitch gets raised, higher frequencies, and as it's moving away, it goes to lower frequencies. So imagine you were in a city and all the ambulances you heard, all their sirens were getting redshifted, if you will. Their pitch, their frequency was getting lower and lower. You'd say, well, that must have meant that there was a crisis where I am, and now all these ambulances are going to different hospitals. And conversely, if you heard all the ambulances sirens increasing as they all move towards you, that would seem to indicate you're at the center of some awful situation. So the Hubble constant is sort of the master governing parameter that tells us how fast is the universe expanding. We believe all of the universe is expanding, and we can talk about what it's expanding into. But for now, let's just leave it at that. Every galaxy we see is expanding away from us. Turns out
you can measure this in many different ways. Hubble used the properties of things called Cepheid variable stars in local galaxies, nearby galaxies, to extrapolate that the universe was expanding once and for all. However, the value that he got was a wild overestimate. He was saying that the universe was expanding about 7 times faster than we believe it actually is. That's a huge overstatement. And so he made a tremendous blunder, but he was on the right track. And now the precision, so he was off by a factor of 7. Nowadays, there's several different ways to measure this, not just looking at distant Cepheid variables, and we can get into the different ways you can measure it, but as Hubble did, but also using the cosmic microwave background that myself and colleagues use today to get a snapshot of how fast the universe was accelerating at early times, and then predict how fast will it be accelerating in the future.
And so there are, it's basically a number, as I understand it, and it's the units that are important here. It's in a speed per distance, right? So kilometers per second per megaparsec. So for every megaparsec something is, a galaxy appears to be going some speed in kilometers per second. Now,
that's right.
And as you pointed out, it's been observed in many different ways, but the big way that we get these numbers, there's really, as I understand it, 2 different ways we get this number. One of them is by looking at the redshifts of things. You mentioned the Doppler shift and all of that, and the other is through the cosmic microwave background. So the way that the Doppler shift method is used depends on something called a standard candle, right?
Yes, there's several different ways to obtain standard candles. Some are more standardizable than others. It's exactly like candles. I mean, a birthday candle doesn't put out the same luminosity as one of those old-fashioned whale candles that I know you have in the back of your office somewhere.
Right. So the way, okay, if you need to know what a standard candle is, they are these. It's a way of knowing the intrinsic brightness of something as if it were right next to you. Okay, and then by seeing something that, if you know the intrinsic brightness, how bright it really is, and then you look at something through a telescope and you see how bright it appears to you, you can compare those 2 brightnesses, do some math, and find out how far away something is. They are absolutely crucial to figuring out how something is. Now, there's 2 big ways we do it. We're not going to get into it much here. There's Cepheid variables. They get bright and dim in a way that tells you how bright they are intrinsically. And type 1a supernovae, which Adam Riess did, are studied. These are light curves that they are very specific, and we know their physics up close, and so we can estimate how bright they are when we look at them. But since this is your strength, Brian, I want to ask you about the way in which the Planck satellite measures this parameter. Yeah. I don't understand it. I never have. When you can look at the cosmic microwave background radiation and somehow get this parameter, can you tell us how that's done?
Yeah. So let's take a look at the highest precision, most scientific display of the cosmic microwave background.
Yes, that's right.
That's this little guy here. That's our old friend.
Symbi. I call him Symbi.
That's right. You can get these from Particle Zoo, by the way, and Tony and I each get 50% cut. No, we don't get any money from it.
No, don't get any money.
Okay, this is an image of, kind of a God's eye view of our universe, cut out, laid flat, and stitched onto this little stuffed animal. Now, you notice that there's some dots on this thing. It looks like dots. There's some blue, some green, some red even. And what those are the measurements of what's called the temperature fluctuations in the cosmic microwave background radiation, in the CMB. So when we measure the CMB, it's often said it's the 3 degree or 2.7 degree cosmic microwave background. But that's the average of it. So it's like saying the average population has a height of let's call it 5 feet 10 inches for males in the United States, something like that, or 180 centimeters, something like that. But that doesn't describe the individual fluctuations of the population. It just describes the average. So another measurement that you'd like to know is how big is the standard deviation, or the fluctuation about the mean value. And for the CMB, it's these fluctuations that tell us very interesting aspects about cosmology. They tell us, among other things, where was there more dark matter? Where was there less dark matter? Where was there more ordinary matter or less ordinary matter, baryonic matter, in the early universe? And those will correspond to, respectively, There'll be cold spots where there was more matter, and light had to work against the gravitational force field, which was causing it to lose energy as it climbed out of these potential wells, as we call them. And conversely, where there are brighter spots, those are spots where the microwaves gain energy, if you will. They have to climb out of less deep wells of gravitational force on each one. Gravity does affect light, we know through gravitational lensing experiments, among other things. So the size of these spots is another way to tell how far away this surface is. And you do so by invoking not a standard candle as something that explodes can provide for us, whether it's a supernova, a type 1a supernova, or it could be a Cepheid variable changing with time. and you have another way to measure distance to something. So that's if you know the intrinsic luminosity. If you have a light bulb and it gives off a certain amount of watts, and then you can determine how many meters away you are from it by measuring the flux, the luminosity, the number of watts per square meter that falls onto your eye or your telescope. Well, another way you could measure distance, and that could be a crude way to measure distance. I mean, you wouldn't think about that. Like, let's measure the distance to a stoplight by calculating the flux, the number of watts of photon energy that I get as I move closer or farther away from it. That would be a very laborious way to measure the distance to something rather than using just an ordinary meter stick. And in fact, you can use a meter stick. So here's a little official screwdriver that has a length of so many centimeters. Now, as I move farther away from the camera, this gets smaller and smaller. And as it gets smaller and smaller, the angle that it subtends, if I made it into an area, that area would decrease as well. So the size spots of these little fluctuations, they'll change their appearance. They'd be bigger or smaller depending on a few different variables. And one of them depends on how far that sound traveled in the early universe. That's sort of what's called the sound horizon at last scattering. And then there's also the proper distance to the surface of last scattering when these wells were really present in the early universe. We don't see these huge dark matter and ordinary matter wells because places where there was more dark matter have collapsed to form galaxies and clusters of galaxies. So there's a characteristic size scale that tells us about the curvature of the early universe, or conversely, you can assume things about the curvature and you can also use it to measure how far away the early universe was from us. And you can use it also to measure how fast was the universe expanding when this snapshot of the universe's evolution, its sound waves, its density waves, etc., how fast it was evolving with time. And from that, in a very simple model in cosmology, you can extrapolate forward. Knowing it at one time, you can extrapolate all the way back to any other time, unless the model is wrong. And that's the exciting thing. So let me know if that made sense.
It
out
did,
there,
actually.
Tony, too.
I do appreciate that because what I'm gathering from this is that because of the size and the characteristic scale of the size of these temperature fluctuations, we can get a sense of how far away something is at, and from that extrapolate the speed or the expansion rate at that moment. What is that? Is it 300,000 years after?
Yeah,
the Big Bang,
380.
Right,
Yep.
380,000 years after the Big Bang. So we can, but here's the thing: that is a fundamentally different measurement than what we measure when we look at a standard candle.
Totally different.
And
it's like using a ruler to measure the distance to a stoplight versus using the light intensity per square meter. They're as different, radically different as you could have possibly.
And ideally, if you know what you think you know about those two measurements, the light per square meter or the ruler, then you should get the same answer. Right?
Yeah, exactly.
The answer for how far away the light post is, whether you measure it with a ruler or whether you measure it with the amount of flux coming off of it, they should match.
Yeah, and here's what's so fascinating. They differ from each other by 9%. And you're like, 9%, that's not a big deal. They probably each have error bars about 9%. No, they don't. In fact, the cosmologically derived, the ones derived from the CMB, have errors that are sub-percent. And the Cepheid variables, the supernova type 1a, and then, of course, the gold standard of distance is called parallax distance.
Right.
Just as you can measure the difference between the separation of your eyes, hold your thumb out at arm's length, blink your eyes, you'll see an angular shift. That's called parallax.
Yep.
That parallax we measure locally out to the Cepheid variables in local galaxies, and we can use that to calibrate the distance ladder to geometry, to none other than Euclid himself. And I'm sorry with respect to Hubble, but he's not a greater at measuring geometry than Euclid was.
That's right.
And so the point is, we have a very well understood, theory of the diminution of the light's intensity and flux versus distance. We understand that from geometry. We understand that from the Cepheid variables, and things get a little bit more dicey, and you try to understand the properties of distant supernova. Just the question is, how standard are they? And they can't be as good to calibrate your measurement. But again, I said the difference between the CMB measurements on one hand and the Hubble measurements on another hand is only 9%.
Right.
But I forgot to tell your audience this. This is fascinating. The reason that the Hubble constant is also very important is because it's inverse. So 1 over the Hubble parameter, it has the units of time. So remember, the Hubble parameter is those funky units that Tony mentioned: kilometers per second per megaparsec.
Right.
So if you look at it, it's kilometers, which is a unit of length, divided by megaparsecs, which is also a unit of length, divided by 1 over seconds. So you get something which the reciprocal of which has units of time or seconds. If you calculate that, you get an age for the universe. If you use one value that is, say, 13.5 billion years,
wow.
or another one that's like 14.
That's
You're
awesome.
talking about a billion years.
I never.
Yeah,
of
it's
course.
huge.
I'm sorry. I'm interrupt. That's really like basic unit analysis, and I didn't even notice that. You have kilometers per second, which is a speed, but you have kilometers, which is a distance, and a megaparsecs, which is a distance.
Right.
Those can cancel each other out if you convert them, and you're left just with per seconds. You flip that over, and you've got a unit of time that is the age of the universe. Now I should. I'm sorry, but I love it when I just realize something.
It's only
like
9%, right? So imagine you go to the bar and you're 20 years old. You're a month away from your 21st birthday. Do you think any bouncer in the world is going to let you in? Oh, it's just a 9% difference. No, it's huge. It's everything.
Yeah, it is.
And for us too, it's quite controversial, right?
Well, it's also more than that, because not only is it 9%, but the error bars, the amount at which we know these numbers, don't overlap. So
exactly. They don't overlap.
Actually don't agree at all.
They don't agree, yeah. There's no making them agree without breaking one of the two following things. Well, either the way that we calibrate nearby things is not very well understood, and there's something affecting our local measurements, which again, that affected Hubble too, and it was nothing more than, say, cosmic dust and the behavior of this population of Cepheids that he didn't know about. Won't get into those details. I talk about that in my book, Losing the Nobel Prize.
Right.
But you know, as always, dust always makes an appearance, and it does confound both measurements of CMB and of the Cepheid variables in supernovae. However, the measurement of these distant of the cosmic microwave background, the one that's 3 times more precise, we believe is 3 times more precise, that one you would have to do something really weird. You'd have to change. Remember, I said that the diameter, these little spots have a width that depends, a little fluctuation. I'm not talking about the eyeballs here. I'm talking about like
the
a
googly
red
eyes
spot.
are crucial. They have to be.
Yeah, the googly. So the size of the characteristic size scale of these spots depends on the speed of sound at the time at which this snapshot was produced, if you like, 380,000 years after the Big Bang.
Speed of sound?
These spots are the speed of sound. Yeah, the speed of sound is sort of the characteristic that sets the characteristic scale over which things could oscillate. You could have fluid waves in this primordial soup. That was what was happening. You had waves of gravity waves, which are fluctuations in gravity and local gravity, not gravitational waves like LIGO detects, or we're trying to detect with these B-mode experiments. No, instead you had a propagation, just like you drip a drop of water in a cup, or you put some in coffee. We're having an Astro Coffee, right? So drop of cream, it'll propagate out. Those are called density waves. And those density waves travel at something close to what the speed of sound is in that liquid. While the liquid we're talking about in the CMB is the photon baryon primordial soup. So it's a soup of photons and protons and electrons, and those will get disturbed and have ripples in them, and those ripples will form these patterns that are these hot spots and cold spots eventually. And so to change their size and change their properties, you have to change what this stuff is made up of. Now, you can't change the properties of protons. Those haven't changed in 13 or 14 billion years. Photons the same way. But you could add some extra form, some exotic type of light or heat or energy or matter at early times, which then perhaps disappeared. And in so doing, left an imprint that would cause cosmologists to underestimate the Hubble constant, making the universe appear older, than it actually is, compared to the late time measurement. So you could try to reconcile these two, but you have to break the physics that we understand today. And that's why it's such a baffling and heated controversy.
So when you say, I just want to clarify one thing. When you say sound speed, you're talking about the speed with which a disturbance in the medium would propagate.
That's right.
And go from one set of molecules to another. It's the same way sound works in the atmosphere, but they call it a sound speed in a medium because it varies depending on what that medium is, what it's made of, its density, all that kind of stuff. So it's an important it's an important parameter to figure out. Well,
that's right.
Okay, so I think we've laid the case out. We know that we figured out how the cosmic microwave background radiation can tell us this parameter. We've briefly touched on type 1a supernovae and how they can tell us this parameter. So, Brian, and I should point out, one of them happens very early in the universe, 380,000 years after the Big Bang. The other one is happening, present day, really, right? I mean, we are looking at
basically
it's the local universe.
Redshift, yes.
So we're looking at more or less now, maybe a few redshift z's away, which would be maybe a few billion light years, but not too far away compared to the size of the universe itself. So
that's right.
We're making two measurements. One of them is right near us, relatively speaking, and the other one is very, very far away. Mm-hmm. What are your thoughts on this? Do you think we're measuring the same thing? Is there anything to keep the expansion rate of the acceleration of the expansion of the universe the same throughout the history of the universe?
Well, it seems quite perplexing, and it reminds me of when I had my first child. When we took him in for a checkup, I think it was his second birthday, and they have checkups every 6 months until he's 2 years old. And we went in there, and they checked him out, and they measured his height. By then he could stand up, and he's not lying down all the time, right? So he stood up, and they said they measured his height, and I don't know, it was like maybe it was 37 inches or something like this, over 3 feet. And they said, oh, all you do is double it, and that's how tall he's going to be. So now he's under the impression, he found out about that somehow, and he's under the impression he's going to be 2 or 3 inches taller than Dad, and he's all proud of that. And I point out his younger brother, who's less than 2 years younger than him, was even taller than he was at age 2. So he better be nice to him. So it's kind of like that, right? You're trying to predict. Now you could say, well, what the heck do they know about like what my son is going to look like when he's fully grown? Now they don't know anything about him in particular. But they do know a lot about the average population statistics. So they've been doing this for more than 18 years, and they've done it on millions of young boys and young girls, and so they can tell with some statistical significance how likely they are to be accurate. So the question in cosmology is not only to do precision and get numbers down to the more and more decimal points, but it's also to be accurate. What does it mean to be accurate about something? Does it mean that you're always right? No, it doesn't mean that at all. In fact, what it typically means to a scientist, the difference between precision and accuracy, often they're confused, by the way, but precision is sort of how many decimal places you have. So you could make an exquisite measurement. I did this once, Tony. I don't know if you did this when you were in college, but I had a college lab, and I was a hotshot physics major, and we were doing the Cavendish Experiment, which is a famous experiment from, I believe, the 1700s, where you take two masses on a pendulum, and you put them near two fixed masses, and you note the oscillation speed. And then from that, you're supposed to get Newton's constant, which has a value of about like 6.6 times 10 to the minus 7, and newtons per meter. Anyway, I can't do the units off the top of my head, but you out there online can look it up. So it was like 6 times 10 to the minus 7. And I got something like, I was feeling really hot because I looked at but I got 7 times 10 to the minus 6. And it's way off. Like, I couldn't. I was like, did I do it? No, but it was very precise, but it was completely inaccurate. Right. So accuracy is how close to the true value it is. We don't know what the true value is. And so right now the question is, how do you get more accurate results? Not just how do you get more precision. That's reducing the error bars. The error bars are already about as small as they're going to get in some ways for the types of CMB temperature measurements. We're also going to get polarization measurements, which will give us another inkling at the speed of sound in the early universe, and it will also give us some input on the possibility for strange new species to be present. So imagine there was something that was like a photon in that it had very limited interaction
with other fields, but it interacted with matter to some extent. That would be that kind of particle is sort of at some level has been ruled out as a dark matter candidate, as a dark energy candidate. On the other hand, if you look at something like a neutrino, which has almost no mass, we don't know what its exact mass is. That's one of the things we're going to learn from the Simons Observatory and other projects in cosmology. But we know it interacts almost not at all, and 100 trillion of them can go through your body without you feeling it every second. So the question is, could there be some new type of force, some new type of field, some new type of matter, or could it be that we don't understand either the cosmic microwave background data, we're interpreting it wrong, which seems really hard to believe, but could be true, and we've had that happen before. And or we are not interpreting the close-in universe. So there could be a problem with each one, and yet it seems that the evidence is sort of it's wide open. Right now, we feel like we could actually change the physics of the universe in only a very small window of time. You have to change it right when this is happening. Right, 380,000 years. You have to get that physics, totally dead set in order to match everything else we see within a span of about 10,000 years out of 380,000.
That's a tall order, I think.
It is, and you go back earlier and earlier, it makes things worse. And then you have other data sets that are coming in. And so I didn't mention, but there's an exact effect that occurs very analogous to the CMB, except the CMB is only a two-dimensional image. We just get the image of how this face or the surface of the universe at this scattering surface presents itself to us. There's something called baryon acoustic oscillations, BAOs.
Oh, yeah.
So if you go out in the universe and you look at all, what's that?
Those hurt my head, but go ahead.
Yeah, but it's actually the same exact physics as the CMB. Pretty much, it's waves of sound, except instead of counting blotches of the CMB photons, you're actually counting galaxies. So if you make this, if you make a certain type of image and you go around and look at all the galaxies in the universe, you notice certain patterns. We call them correlations. And you notice that there's a characteristic scale at which these galaxies are producing the highest levels of correlation. And that's called an acoustic or sound horizon at that redshift. The benefit of galaxies is that, as you know, you can look at a star. Let's say there's a star in this galaxy, right? This was taken by Margaret Burbidge, by the way, my colleague who's 100 years young as of the recording, and she's quite a phenomenal astronomer. So I have actually her late husband's old office, and if you look at these plates that she left us to look at, you'll see stars in them, and so you can use these stars to measure the distance to this galaxy, and you could do that for all the galaxies all over the entire sky that you can measure, and that's what the Sloan Digital Sky Survey and other surveys have done, and they've done phenomenal work that show as a function of redshift how is the Hubble parameter changing as a function of redshift. In other words, they have an independent measurement that agrees with the cosmic measurement down to the redshifts at which the Cepheid variables are being measured. So it seems, if I had to put my money, of course I'm biased. I work in cosmology in the CMB, and so I might be more inclined to think that there might be an error in the optical starlight and Cepheids and supernova data, and to point out how hard this is. So when you talk to your buddies at Space Telescope, if you ask them, well, how much would you have to change? How much would you have to change the properties of the stars that you measure? In other words, how much would the brightness have to change to be in concordance with the cosmic measurement?
Right.
Do you know how small it is? It's only a fraction of a magnitude, so it's about 0.1 or 0.2 magnitude.
Oh, really?
You
that's
shift each one. Yes, it's nothing, right?
It's that sensitive to the parameter of the Hubble constant.
That's the level of magnitude, literally. I'm sorry to use the same word for two different things. Magnitude is a measure of intrinsic luminosity of these subjects. And so is it hard to think about them getting all the magnitudes wrong, all the intrinsic luminosities, which have to come from models, by the way, which are not as sound, perhaps, as models of the earth, just literally the speed of sound in the early universe. We understand fluid waves very well, whereas, saying a supernova, which we can't put in our laboratory, it's purely understood theoretically, how these type 1a supernovae behave, could that be an issue? And a lot more data is going to come in, and they'll always be a little bit less precise, or maybe significantly less precise. So there won't be as many decimal places as the CMB and the cosmic measurements. So if I had to put my money, now again, these are magnitudes. You're shifting, a fraction of one magnitude out of something which might have an observed magnitude of 20 or something, some apparent magnitude of 20.
These are
So
already
in other
very
words,
dim. Yeah.
it's incredibly dim, and
Right.
it's such challenging work.
Well, that's okay. I want to drill down on this just a little bit because I've heard the same thing. I'm inclined to agree with you about this. I think there's something about these Type 1A supernovae that are wonky, and I've seen some discussions on it. I've read some articles on it. But you've recently talked to Adam Riess about this. Now, Adam Riess got the Nobel Prize based on his Type 1A supernova work. What does he say about that?
Well, he is, not surprisingly, and not to say he's biased in any way, but he has a great deal of confidence in these measurements. Adam is such a phenomenal scientist. A lot of people
Right.
say things
He's a nice
that
guy too.
yeah. Once you win a Nobel Prize, T.S. Eliot said after he won the Nobel Prize that he was upset about it because no one ever did anything worthy of anything after he got it, after they got it. So he was pretty. But Adam, I go to meetings with him. I've had pleasure long conversations. He works 24/7. This
does.
guy, you'll see him at a conference. He's doing Python coding. He's looking up data. He's talking to students. I mean, he just doesn't quit. And it's hard for him because there are people publishing papers all the time that he was wrong. The Nobel Prize was given in error. And I don't agree with that. But you have put a big target on yourself when you do that. Adam's a top-rate scientist,
Yeah.
and I think what he's saying is that we can hope to do better. It's really hard. It would be nice if God, or if you like Mother Nature, could ignite a supernova at redshift of 10 that was just amazing, perfect standard candle that came with a little Sylvania light bulb sticker on it. This is how many watts I'm putting out. But until then, there's a lot more modeling that has to be done. He's also getting involved with other ways to measure this. And in fact, some of the ways to measure it in a local universe, again, he agrees that the distant universe measurements, that's not his forte, although he has looked at data from the Planck satellite. And I should point out, there's two completely independent measurements of this effect from satellites, which are the gold standard for most of these, WMAP and Planck, and they both agree, and in fact, Planck gets a better result because it's much more sensitive and higher resolution. So things are moving correctly and insanely as we're proceeding. Yeah. So I think he's confident in our measurements. The question of convincing us that we should be confident in their measurements is a tall order, but there's a lot of hope on the horizon, and that's because of new techniques. In particular, we talked about standard candles, which are sources of supposedly known intrinsic luminosity. So
That's right.
Light bulbs that have 100 watts stuck on them, but they're in the form of stars or supernovae. And then we talked about standard rulers. Things have been exactly known, calibrated in distance, and we know how long they are. So moving them away, you can calculate from their angular subtending, the angle that they subtend, how far away they are. Well, there's another way you could do it, and these are called standard sirens. And these are black holes spiraling on one another.
Yeah, I'm glad you
that will
mentioned
create, hopefully create a characteristic waveform for detectors like LIGO and Virgo to measure. So that's another way that we can get at it. There's a fourth way, which is called time delays. So as light gets gravitationally lensed as it goes through a massive dark matter well or cluster of galaxies, an event, you see some flash of light over here, you'll see two images of it, but they'll be delayed in time by so many days. You can actually use that time delay to measure the Hubble constant. That's a fourth way to measure it. There's a fifth way to measure it, which is using what are called masers, which are distant natural sources, kind of like lasers, but they emit microwaves instead of visible light waves, and they occur naturally in outer space in distant galaxies. And you can use those to measure distance and to measure time delays. If you know the intrinsic frequency, which are very well understood, just like lasers are, we know their frequency exactly what a helium neon laser produces. And it's the same here on Earth as it is on some planet orbiting in the Andromeda galaxy. So those are standard masers. That's a fifth way, and there may be many other ways to do it in cosmology that colleagues and friends are working on. So I think the future is bright for something so dim as measuring these distant objects in cosmology.
Well, you just answered, I think, ASCII's question, which was, can gravitational astronomy shine more light, pun intended, on the issue? Not the LIGO, but the LISA. So when you're talking about these standard sirens, that's what you're talking about, using gravitational
Exactly.
wave
Yeah.
astronomy.
Yeah. The ripples in space-time get delayed and deferred depending on how far away and what the properties of expansion have been since emission to reception.
Okay, but can LIGO do that, or are we going to need LISA?
No, LIGO can do it. Not on any individual source, I'm told, but with a nice statistical sample, they can actually get to comparable precision. Not quite the 3 or Actually, Adam's at 1% precision, I believe, on his supernova, and Cepheids. I think they can get to 3 to 4% precision. But what's interesting and what's really important is that we want to use as many different techniques, not just get higher and higher precision, because there are things called degeneracies. Certain things are degenerate, shoe size and height. Does that mean, are you raising your hand, or
Yeah,
you want to?
I'm a degenerate. No, I'm kidding. I'm kidding.
No,
Go ahead.
no, not at all.
I love that thing.
You're addicted to cosmology.
I just love
So,
saying degenerate. That's all.
Yeah, that's right. So there are things that have the same types of behavior that aren't physically related to one another. I think what's important is that you break those degeneracies. You find as many different ways to measure the same thing. You let thousands of flowers bloom, because each one can have very low precision, in some level, but by having a bulk of them, many more of them, you will actually get a higher level of net precision if they're not degenerate. If you keep measuring the exact same thing over and over again, it's 100% degenerate, and so you'll never improve beyond the intrinsic uncertainties of the limiting measuring device.
Okay. I'm going to get to Hans Milling's question. By the way, Hans, thank you, man, for helping support the channel. It means a lot to me. Thank you so much. You're a regular, and I love having you here. But I'm going to read you his question. He's asking, I've heard the dark spot in the CMB is another universe touching or bouncing into ours. Does Brian believe this?
No. So there are no currently. What he's talking about is that there appear to be some regions of the microwave sky that have anomalously low temperatures. In other words, there are many more standard deviations or variances from the mean temperature of the CMB, which is 2.726 Kelvin. There might be something that's 2.736.
Oh, wow. Did you just die? Oh, he left my session. Hopefully he'll come back. All right, well, while we wait for him to come back, let me do this. Sorry for the technical difficulties on this stream, guys, but I had a video capture card die, and I usually split Zoom and Wirecast into 2 laptops, and I feed the one laptop into the other, but my capture card that does that died and prevented me from doing it. So I had to try this new system, which is there's something called Rendezvous in Wirecast, and I can have guests, but it's like this. It's very, very twitchy, and I'm sorry about this, and thank you for bearing with me on all the technical issues. I do apologize for that. Let's see. So Allison Walker, you're asking, the speed of sound was slower or faster in the past? I wish you were here to answer that, but it would seem to me that because of the sound speed is based on the density and the properties of that particular, whatever that particular medium is made of. In the case of the CMB, it's the universe, and it contains both hydrogen and all of the elements of the universe plus dark matter. And it was also in a much smaller area in space. My hunch is that it was faster because of the density, but I don't know the answer, and I'm sorry he's gone away from us. So sorry, Allison, I don't know the answer. If he comes back, I'll ask him. So thanks, ASCII. I appreciate it. It's anybody who follows these hangouts for any length of time knows that the production quality here at Deep Astronomy HQ has been very wanting. I try my best, but I don't have very much stuff. So I did spend some money on some software like Wirecast and other things, but it's sort of my equipment is starting to show its age. Okay. I'm not quite sure where he went. He's left. He might have gotten cut out of the session. So at any rate, I'm going to go ahead, and we didn't quite get to a full hour because of the technical issues. but I'm going to go ahead and probably stop this while we're still reasonably ahead. A couple things to note. Next week there will not be a stream because I've got other commitments I have to deal with next week that keep me from being in my home. I'm going to have to do some. I'm going to have to be somewhere else next week to help out some family members because of all this stuff that's happening lately, and so I won't be able to stream next week, but I will be back. That includes Tony, T Cubed, which is Tony's Twitch Tuesdays, but I will be back the following week back to streaming. And in the meantime, I'm hoping to set up and have going a 24/7 live stream with my content looping through it, and we can chat, and I can come in, and that will allow me to come in and out when I can from whatever location I'm in. So, again, guys, I appreciate you guys' patience on this. I wish Brian was here to answer your questions. You're asking questions I don't know the answer to, so I can't help you. Like Allison, you're going, I think I heard that as well on PBS Spacetime. Heard of SOFAR channels in the ocean? Why the whale sounds travel so far? Yeah. So anyway, I thought it's my intuitive understanding of how sound, what they mean by sound waves. They're not really talking about sound, by the way. They're talking about disturbances, oscillations in the medium, how fast they travel. In a dense medium, they would travel faster than in a slower medium. So sound speeds, they'd use that term, but they don't really mean sound, although sound is a disturbance in our atmosphere. And the way it propagates is at different speeds depending on where it is. And so it is, when you know the sound speed of a medium, you can know what something is called its scale length, which is how, a characteristic scale over which you can measure distances in that medium. And it's a very handy thing to use. They use it for solar physics. They use it in solar wind. They use it in the atmosphere, obviously, and they also use it in nebulae and now in the cosmic microwave background. So, anyway, I'm sorry about the technical difficulties on this one. I'll get them ironed out before the next Hangout. And thank you all for watching and hanging in there for me. I appreciate it. And we will see you in 2 weeks. I'll be back. And thank you all so much for watching. And as always, keep looking up.